Hello everyone, I am Suvrat and we'll be discussing Starters 221 today. So let's start the discussion. Problem A, odd string. You are given a string s of length n consisting only of lowercase English letters. A string is called an odd string if and only if for every pair of indices I less than j such that si is equal to sj, the distance between them is odd, that is j minus I is odd. In other words, no two equal characters are allowed to appear at an even distance from each other. You are allowed to rearrange the characters of the string in any order. Determine whether it is possible to rearrange this such that it becomes an odd string. So, problem A. Basically, we are given a number and we can apply the following operations on it. First is, okay, so we are given a string and we can apply the following operation on it, that we can rearrange the string and for every pair of indices I less than and we need to tell if it is possible to make the string an odd string or not. And the definition for the odd string is that for every pair of indices I less than j such that si is equal to sj, the distance between them is odd. So if si is equal to sj, then j minus I must be odd. So the constraints for this question is n is less than equal to 100 and t is less than equal to 10. So the expected time complexity would be, I think, maximum of O of n square, because O of n square would be 10 to the power 4 and then 10 to the power 5 operations, and O of n cube will be 20 to the power 7 operations. So I think even n cube will also work. So now let's see the test cases. So the first test case is A, and since there are literally no two indices where si is equal to sj, then this condition is valid. So the given string is already a odd string and we don't need to rearrange the characters. So the answer is yes. The next is BB, and since there are only two characters and they are both the same, so the distance between them is 1. And since 1 is odd, the answer for this is yes. Let's see the next test case, XXXXX. So it doesn't matter how we rearrange the string, since all the characters are the same, so it would be the same after rearranging as well. And let's see if this is an odd string or not. So these two are the all the indices are all si are x only. So the distance between any two indices must be odd, and that cannot be possible. The distance between them, these two, is 1. That is fine, and distance between these two is also 1. That is also fine, but the distance between these two is 2. So that is not fine. And so because of that, the answer for this test case is no. And looking at this test case, we can make a quick observation is that, let's say we have some character x, and then we have another x, and then we have another x. So in order for this string to be an odd string, let this distance be d1 and let this distance be d2. So d1 must be odd and d2 must also be odd, and d1 plus d2 must also be odd, right? For the string to be an odd string. But when we add two odd numbers, we get an even number. So if we assume that d1 is odd and d2 is odd, then this statement would be invalid, because if we take any two odd numbers, for example 3 plus 5, then the summation would be an even number. And we can also prove this because d1 plus d2, when we take modulo 2, this becomes applying the property of a plus b mod m. equal to a mod m plus b mod m whole mod m. So if we apply that property here, so we get d2 mod 2 plus, sorry, d1 mod 2 plus d2 mod 2 whole mod 2. And we know that d1 mod 2 will be 1 and d2 mod 2 will be 1, since we are assuming that d1 and d2 are odd. So 1 plus 1 whole mod 2, and this comes out to be 0. So if d1 and d2 are both odd, then d1 plus d2 must be even. So based on the fact that if d1 and d2 is odd, then d1 plus d2 must be even. We can, based on this fact, make this observation that there cannot be three or more characters in the string which are same. Because if there are three or more characters which are same, then there would always be this case where the distance between these two is odd, these two is odd, and hence the distance between these two will not be odd. So it cannot be an odd string. So we made this observation. Now let's move on to the next test case. So AA, B, CC, BD. So we can see that our statement is valid, that there are no characters which appear three or more times. So let's try to solve this problem. AA, B, CC, BD. So we have A two times and B also two times and C also two times and D one time. And we need to rearrange and place these in such a way. For now we can see that the distance between these two is 1, that is fine. Distance between these two is 1, that is also fine. But the distance between these two is not 1, it is 4. So that is not fine, since all the distances between two same characters must be odd for the string to be an odd string. So we need to rearrange these letters so that the resulting string is an odd string, and we can see that if the two same appear consecutively, then the distance between them is odd. So what we can do is, based on this, devise a strategy like this to solve this problem. So we can place AA, and then we can place CC, and then we can place BB, and then in the end D. So that way all the same characters would be adjacent and the distance between them would be always one only. So based on this algorithm of constructing a string which has all the pairs at odd distance, and given that there are no characters which appear three or more times, so we can use this strategy to always find a string where the distance between any two same characters is always one only, because they are adjacent. So we can say that if frequency of every character is less than or equal to 2, then the answer would be yes. Since we can always follow this strategy, we can follow this strategy to construct the answer, to construct the odd string. So let's see the next test case. So next test case is AABCC BDC, and now we see that C has appeared three times. So that violates our condition of every character being less than or equal to two times in the string. So the answer for this is no. Then the next test case is ABCD ABCD. Here we can see that all ABCD have a frequency of 2, and we can now construct a string like this: AABB, CC, and DD. And in CodeChef also, C appears twice, O appears just once, D appears just once, E appears twice, and H and F also appear just once. So again answer is yes. A, B, C, D, E, again answer is yes. So the solution to this problem is simply checking if the frequency of every character is less than or equal to 2. For this, what we can do is, we can make a we can make an array of 26 length to store the frequency of each character, and initially it will all be initialized with 0. And then what we can do is, for every character in S, we can just add that character in count. So do it like this. So after this for loop, we will have the frequency of each and every alphabet in the string, and that will tell us if it is a valid string or not. So for that, we can just simply do this. Perform the check if CNT of I is greater than 2, then simply answer will be no. So this is an O of n for loop, and this is O of 26, and then this is also O of 26. So the overall time complexity for this problem would be O of n, which is well within the time limit. So let's see the code for this. So I take n and string s, and then I create this CT array to store the frequency of each character, and then I initialize it with 0, and then for every character in S, I increment it in the CT array, and then I'll be iterating over the CT array to check if any character has a frequency greater than 2, and if yes, the answer would be set to false, and in the end, I can just check whether my answer was set to false or not. If my answer was true till the end, then I will see out no, else I'll see out yes, else I'll see out no. So that was the solution for problem A. If you guys have any doubts, you can ask. No, I was not able to solve ENF. I actually was not at home, so I didn't actually give the live contest today. C, I solved with a long casework actually. I mean, not very long, but yeah, I didn't find that problem very enjoyable. All input are going up to 1 9. I don't think brute force will work in C. Kind of brute force, but we'll see. We'll see when we come to C. What does CNT C minus A do? So basically, um, every character is treated as an ASCII integer. So basically, C, when I try to perform this operation, the compiler looks at this and goes like, two characters cannot be subtracted, right? So obviously, what it does is it converts them into the ASCII corresponding ASCII numbers, and then subtract those two. So if we look at ASCII table, so basically C would be coming here. So it is uppercase, right? I think. No, it's lowercase. Okay. Yep, lowercase. So basically, you can see that C comes here. So its nine. Its value is 99 in the decimal, and the value of A is 97 in the decimal in ASCII table. So when I try to C minus A, it would just do 99 minus 97. That is 2. So basically, when I write this statement, I'll just get 2 if the current character is a C. And let's say if the current character was a J, then I would simply get 106 minus 97. So that would be 9. So basically, all these would go from 0, 1, 2, 3, 4 till 25. So you can use that trick to calculate the frequencies of each character. So I think we can move on to the next problem. Okay, so the next problem is odd operations. You are given an integer n. You can perform the following two types of operation on n. Digit subtraction. Choose any digit present in the current decimal representation of n and subtract it from n. Digit reordering. Rearrange the digits of n to form a new integer. Leading zeros are not allowed. For example, 1067 can be rearranged to 7106 but not to 10670. Also, 90 cannot be rearranged to 9. Determine the minimum number of operations required to make n an odd number. And if it is impossible to make n odd using the given operations, print -1. So problem B. So basically we are given a number n, and we can perform the following operations from it. So first operation is n changes to n minus d, where d is a digit in n. And the second type of operation we can do is digit reordering, rearrange the digits of n to form a new integer. So we can rearrange n to form a new integer, comma. Also, leading zeros are not allowed. Leading zeros not allowed. So what we need to tell is the minimum operations to make n odd. And the constraints are t is still 1e5 and n is still 1e9. So the expected time complexity might be something like O of log n, because anything more than that will give TLE. So let's see the test cases. The first test case is 246. 246. So this is currently an even number, and we can perform two types of operations. So first we can either rearrange it, or we can subtract a digit from it. So let's try subtracting a digit from it. So let's do 246 minus 6. So that would give us 240. And then again, since the number is still even, so what we can do is let's again try subtracting a digit. So let's now subtract 4. So this becomes 236. But now we see that still the number is even, but we have got an odd digit. So what we can do is we can apply the second type of operation. We can rearrange this number to 263, so that this odd digits comes to the end. And if the odd digit comes to the end, then basically the number would have become odd. So this was the first operation, this was the second operation, and this was the third operation. And if we try to do it in less than 3 operations, so obviously one operation will not work on this, because the all the different type of operations that we can perform is either this or this or this or rearranging. So all four will not give us an odd number, so answer could not be 1. And we have a way to get the answer as 3. So let's see if the answer can be 2 or not. So for 2, we have two options. We can first rearrange, and then we can subtract a digit, or basically we can rearrange then subtract. This could be 1, or we can subtract then rearrange. This could be 1, or we can subtract, and rearrange is not a clever way to approach this problem. So if we try to rearrange then subtract, so what can be the different possible outcomes? So they can be 246, 264, 462, 426, 624, and 642. So basically, no matter how we rearrange, the end digit would always be an even, and we can only perform one more subtract operation, and that subtract operation would be another even number only. So even minus even kind of thing we are doing, and this result would always be even. And we can again use the similar kind of proof that we did in the last problem. Basically, we can again use this property to prove that even minus even would always be even. Also, we can just simply do it like this: even minus even by 2 would be an integer, because it is simply even by 2 minus even by 2. So difference of two integers in an integer. So this will not work. And if we subtract then rearrange, then again for the same reason it will not work, because after subtracting the number is still even only. And since we are subtracting without rearranging, so we only have three possible choices of 246 minus 6 or 4 or 2, and all of them would just give us the numbers 240, 242, or 244, which are all three even numbers and all the digits are even, so we cannot rearrange to make this an odd number. And again, 2 times subtract would also not do anything, because it would be just even number currently minus an even number and then again minus an even number, so it would not work. So we can say that this 3 is our best possible answer. So the answer for this test case will be 3. And so we can make a few notes towards the answer. One of them would be, if we have a single odd digit in the number, then we can rearrange the number to make it odd. So that will be one operation only. Next is that, obviously, if the number was even already, then that would be zero operations. Let's see if there is any other case where the operation could be one. Let's first, for now, just continue on the test cases. So the next test case is 1 0. So 1 0. Here we see that. So what we can do is we can subtract this one here, and then again this number will become 9. So that is an odd number. Also, if we have a single dollar digit, then we can either rearrange it or we can do even. So the number was currently even, right? And we can subtract that odd digit from the number. So that would make the whole number odd only. So we can either rearrange the odd digit to be at the last, or we can do this subtract operation to make the number odd. So here in this case, since we are not able to perform the rearrange operation, since that would place 0 as a leading 0. So, but what we can do is we can subtract this one so that this becomes 9. So again, answer is 1. Then for 8, actually there is just one single type of operation that we can perform, and that would be just 8 minus 8. So that will give 0, which is an even number, and we cannot perform any further operation. So the answer for this would be -1. And then for the next number 343, it is already odd, so the answer is 0. Then the next number 42. So 42, we can rearrange it to 24 maybe, or we can do a -4, that makes it 38. And then rearranging this term will give us 83, which is an odd number. So again, answer for 42 is 2 operations minimum, because there is no way we can do it in one operation. Again, basically what we are doing here is, if we look at this process carefully, what we did was, we subtracted 4 from this 2, so that this 4 becomes 3, because it needs to give the carry to this 2. So when we subtract 42 minus 4, what happens is, basically, since this 2 is smaller than 4, we need to get a carry from this 4, and then 12 minus 4 would become 8, and then we get a 3. So if this number was even before, then it becomes odd in the next step. If we are subtracting from a digit, we are subtracting a digit which is greater than the last digit. So that would reduce the digit at the 10th place by 1. So we can actually now try to solve the problem. So we can break the problem into specific cases, so that we can use these observations. So first of all, for the case when answer is 0, we can simply check if n percentage 2 is equal to 1. Then the answer is 0. For the case where answer is 1, there must be at least one odd digit. Now for the case when answer is greater than 1, So that means we have to perform multiple operations. So for the case where the answer was 2, we can look at this specific example. So what we did was, since we had this 4, we subtracted this 4 from this 2 to make it 38. This 4 from this number 42 to make it 38, so that this digit gets odd. So basically now after these two special cases, we need to only focus on when there are when all the digits are even. So we just need to focus on that. So since all the digits are even, let's just focus on the last two digits, the 10th and the 0th digit. So this will be some even digit and this will be some even digit. So if I subtract from a digit d, which is, let's say, greater than e, so what will happen is this e will have to give a carry. This, let's just say this is even, this is e2. So if d was greater than e2, this e will have to give a carry, and only then subtraction would be possible. So the 10th place will become even minus 1, which is now an odd number, because obviously previously this was even and minus 1 would make it odd. So also, even if this was 0, so the number must look like this, right? 0, 2. So after performing the subtraction, this will become 9 and this will become 12 while performing the subtraction, because this, even this must get its carry from somewhere else, right, and make it 10. So no matter what, if this is an even number and we subtract it from a digit which is greater than e2, then this digit will decrease by 1 and it will become an odd digit. So what we can do for the case where the answer is 2, if there is a digit in n which is greater than the last digit, we can subtract that digit and then rearrange, or basically, since after we subtract that digit from n, we are now at this case that there is at least one odd digit, because we know that the 10th place will now be odd only. So after this 2, we will be again at the case where there is only one operation required. So sorry, after this one operation, we will add the case where only one operation is required. So the answer for this case would be 2. And now there is one more case where there is no other digit which is greater than the last digit. So again, so obviously we'll not be able to perform this in 2 operations, right? So let's try to do it in 3. So if we notice one thing, that let's say that the last digit was the maximum. So obviously we cannot do it in 2 operations, but we can we do it in 3. So we can actually split this 3 operation into 2 plus 1. And so the aim of the first 2 operation would be just to introduce a odd digit. And to introduce an odd digit, we need to subtract the last digit from a digit that is greater than it, right? So what we can do is, let's say that the last digit was e2 and there was some number. So what we can do for the first operation, we can simply subtract this number by e2 only. So that will make this number this and then a 0 in the end. And since 0 is the smallest possible digit, any digit that is here would be greater than 0, and we can simply now subtract that digit and we will get an odd number here at this position at the 10th place. So since after we have introduced this odd number, we can now make one operation and get the final result as odd. So basically, if the last digit was the maximum, then the answer would be 3. Or if there is some other digit that is greater than the last digit, then the answer is 2. If there is at least one odd digit already, then the answer is 1. And if the number was odd from the starting, then the answer is simply 0. So that covers all the cases, all the possible cases for n, and we can use this in the code to get the correct answer. And the time complexity would be, since we need to check upon the digits of the number n, so we can do this in O of digits. So that is approximately O of 10, which is a constant time complexity. So that would be well within the time limit. So I'll show you guys the code for this now. So, okay, and the case for -1 is simply if n is less than 10, because if n is less than 10, we fail to do this thing, because after we subtract e2 from e2, this last digit becomes 0, and but the other thing is that we don't have any more digits that we can subtract from this number, because all of these are 0. So for numbers that are less than 10 and even, the answer is -1. Then what I'm doing is, I followed this simple algorithm to get the digits of n. So I am getting the last digit of n by doing n remaindered by 10, and then I simply floor divide by 10. So we can see this process. So if the number is 1 2 3, what we'll do is n percentage 10 is 3, and n after floor dividing by 10 will become 12. And again from 12, n percentage 10 will be equal to 2, and floor divided by 10 will give us 1. And then n percentage 10 will give us 1, and floor divided by 10 will give us 0. So we'll get the digits 3, 2, and 1. So I am getting the digits like this, and in the end I am reversing to get them in the correct order. And so if already the last digit is an odd digit, then the answer would be simply 0. Otherwise, I'll need to check if the answer is 1, 2, or 3. So for the answer to be 1, there must be at least one odd digit, right? So I'll run this for loop to check if there is at least one odd digit or not. And if after this for loop check comes out to be true, then that means one odd digit was found and the answer would be simply 1. But now if the answer is not 1, then I need to check if the answer is 2 or not. So for the answer being 2, there must be some digit which is greater than the last digit. And if we find some digit that is greater than the last digit, then we again mark check as true. And if check came out to be true, then the answer would be 2. And else, if none of this was true, then the answer would be 3 in the end. So that was the solution for problem B. If you guys have any doubts, you can ask. Okay, let's move on to the next problem. Yes, that is right. So the next problem is rectangular coloring. You are given a rectangular fence with a length L and width W. The fence has four sides and the total length of the fence is 2 into L plus W. You have exactly enough paint to paint the fence using the three colors red, green, and blue. So that means the total available paint of each color be RGB respectively, then R plus G plus B is equal to 2 into L plus W. Each unit of paint can cover one unit length of the fence. Painting cost: each side of the rectangle must be painted completely. A side may be painted using one or more colors. The cost of painting a side is equal to the number of distinct colors used on that side. Determine the minimum total cost required to paint the entire fence. And the constraints for this problem are, everything is up till 1e9, and there are 1e5 test cases, so expected time complexity would be again O of log 1e9. So log type time complexity would be required. So let's see the problem. So problem C. So in this problem, we are given a rectangular fence of LW, LW, sides, and we are given three colors RGB, and the total units available for these colors is equal to 2 into L plus W. So after this, we need to paint this fence, right? And the cost, and we need to minimize the cost of painting the fence. And the cost is defined as follows. So the cost is cost of each side of the fence is equal to number of different colors on that side. So that would be the cost for each fence would be somewhere between 4. For now, what we can do is simply let's just start from this point, and let's just start placing the colors one after the other. After one ends, let's just continue to put on the next color. So the we have 9 units of red color, so it would be, so we'll be able to complete this side of the fence and also this side of the fence. And then we have 5 units of the green color, so till here. And then we have 4 much. So the total cost that comes out to be will be 1 plus 1 plus 2 plus 1. So that is 1, 2, 3, 4, 5. So now, since the minimum cost that we could have gotten was 4, right? We saw that each side the cost would be ranging from 1 to 3. So the overall total cost must range from 4 to 12. So we need to see if there can be, the cost can be 4 or not. For the cost to be 4, the color must be like this. This must be of one color, this must be of one color, this must be of one color, this must be of one color. So each side must be made up of just one single color, and we have three colors, comma, four sides. So if we have three colors and four sides, so there must be one color which colors two sides, and the remaining one color will color just one side, and one more color will just color one more side. Only in this way we can get that, we can make sure that each color, each side has the same color, because there cannot be one color which takes up three sides, because we need to use up each color, and we are given that each color is greater than equal to 1. So there must be one color that takes up two sides. There cannot be two colors that takes up two sides, because then the third color we will not be able to use. So one color that takes two sides, and other two colors take just one side. Only in this case the answer would be 4. So here we can see that 9 can take up two sides, which are 6 and 3. But if we try to allot this 6 and 3 to this 9, then the 5 and 4 don't actually color these sides individually. And similar, and when we try to color two sides from 5, we are unable to. And similarly, when we try to color two sides with 4, we are again unable to. So 4 cannot be an answer. So in this case, 5 must be an answer. So actually, also, let's write this as an observation for answer equal to 4. Let's see the next test case. So the next test case is 44484. So L equal to 4, W equal to 4, R equal to 4, G equal to 8, B equal to 4. So we have 4444, and we can see that now actually it fits the description of this case where one color can take two side and the other two colors will take one side. So what we can do is, using this green we can take up these two sides, and then using this red and blue we can take up this side and this side. So this test case actually proves our theory for for when the answer can be 4, and that is the minimum answer. So we don't need to check anymore. So the answer for this test case is 4. Then 23118. L equal to 2, W equal to 3, R equal to 1, G equal to 1, B equal to 8. So we have 2 and 3. 2, 3. So one thing we can point out is that again the answer cannot be 4, because there are no two sides that we can color using any of this. If we try to use 8, then 3 plus 2 5 plus 3 8, we can actually color all these three, but then there are no two sides for these two to color. So again this is 8 can sorry 4 cannot be an answer. But we can see that since this 8 takes up these three, then R and G will just take up this leftover R and G. So the answer will be 5 in this case, because 1, 1, 1, and 2. Let's see the next test case. 3, 3, 1, 10, 1. L equal to 3, W equal to 3, R equal to 1, G equal to 10, B equal to 1. So we have 3, 3, 3, 3. And now we have G as 10. So let's just do this. And then we'll have to go 1, 1. And actually, we cannot do any better than this. So the answer for this would be 1, 2, 3, 4, 5, and 6. 4, 5, and 6. So actually, let's just use this approach. Let's say we have got some rectangle L, W, and what we'll do, we have some values of R, G, and B. So let's just start from this corner and fill it up using R as much as we can, and we'll stop when we have consumed all of the red color, and then we'll just continue from this point and use the green color, and then we'll continue from this point and use the blue color. So actually what we can see is that there will be only 2 points where the two different colors meet each other. So there will be, since only 2 points, so only for these two sides the answer will be 2 2, and the other side's answer would be 1 1 only. So if we simply use this simple strategy, we will be able to color our rectangular frame in just 6, what was that, 6 score. Because we saw here also, since this was green, we just started from this point and we used up one color, but then the next and then the next, and we saw that only two intersections happened, and because of these two intersections the answer increased by 1 due to this and 1 due to this, because here two different colors were on this side and again another different color on this side. So overall 3 more, so overall the answer came out to be 6. So what we can see is, if we follow this simple strategy, we'll be able to get the answer 6 on any type of rectangular frame. So actually we can make our answer from 4 since we had previously from 4 till 12, what we can do is make it 6, because if the if we follow this simple strategy of just placing the colors from one corner and start using the next color after we are done with the first color, we will be able to get the score 6. So our answer must be less than 6 only. So now what we can do is, since we have only three different possible choices for answer, 4, 5 and 6, and we already have a strategy to check if the answer is 4 or not, what we can do is we can just check if the answer is 5 or not. If the answer is 5, well, then the answer will be 5. And if the answer is not 5, then the answer will be 6. Because for 6, we have a strategy that will always work. So our problem now boils down to just finding whether the answer can be 5 or not. Find whether the answer can be 5 or not. So if for the answer to be 5, basically, let's take some grid. So for the answer to be 5, since when there were two intersections, the answer was 6, right? So two intersections cannot happen now. So we need to do the answer in just one intersection. So that means that there must be some color that fills up exactly this much, and then another color that fills up exactly this much. So if there is some pattern like this, then we can ensure that this is zero intersections, right? So what we can do is, for there to be one intersection, it must be like this: green and then blue. In only this case there can be one intersection, because there must be at least one color that does not intersect with the next color. So what we can say that there must be one color that does not intersect with other color. So here we can see that the red does not intersect with green or blue, because it starts with this corner and it ends at a corner, so it does not intersect with any other color. So in this case, we can say that the maximum answer we can get is because of intersection of blue and green, and that would be at max one intersection, obviously. So the answer for these type of cases would be 5. So what we need to check is that if there exists some color that we can ensure that it does not intersect with any other colors. So basically, we need to find if we can ensure one of the colors starts and ends at a corner. Because if it starts and ends at a corner, then there cannot be any intersection. So what does starting and ending at a corner mean? That it can color a subset of edges. It can color either just one edge completely, or it can color two edges completely, or it can color three edges completely. For example, if we had like this, so let's say that red could have colored these two edges completely. So now we know that red does not intersect with any other color, and we can just start at this corner, start placing green till we can place it, and after we are ended with green, we can now place blue starting from here. So obviously we'll get a maximum of one intersection, and the answer will be 5. So this was the case where two edges could be colored by red, and even if the two edges are like this, again the answer is 5 only. And if we see that, we can also see that if there is just one edge that can be colored by red, again we'll be able to just do green, 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 and then blue, blue, blue. So again, just one intersection, so answer will be again 5. So we just need to check if there is some color that can color a subset of edges. And for 4, we can see that there must be one color that can color two sides, and one color that will just color one side, and another color will just color one side. So we can now brute force over this because the dimensions are quite small. So first of all, for this, what we can do is we can brute force over the two sides that can be, we can actually brute force over R, G and B, for which color would be used to color the two sides, and we can again brute force over the two sides that can be colored. So there, since the number is so small, the brute force will be able to work it out in the, and here also we can use a simple brute force to check if there is a subset of edges. And what we can do, since there are four edges, right? So let's say that a number like 0101 will represent that the first and the third edge are colored by the same color or not by the same color. So what we can do is from 0000 till 1111, we can check for every binary number. For example, let's say we are checking for 1010, so we can take the first and the third edge and we can add the lengths of the first and the third edge, and we can see if any color matches their length, and if yes, then the answer would be simply 5. And that way we can brute force this also. So I'll show you guys the brute force in code only. So what we'll do is I have created an array for the lengths and the columns, and now what I'm doing is this I, J and K is the red, green and blue. So these will represent the three colors that I have. I would be some color, J would be some color, and K would be some color. And since I'm brute forcing and these three must be different, so I'll continue if J is equal to I, and if K is equal to I or K is equal to J, then I'll continue. So at this point, I am now sure that I have three variables I, J and K that take up the value from 0, 1 and 2 each separately, and each of them distinct. Now what I will do is I will select two sides which take up one the same color. So what, for the checking if the answer was 4 or not, we needed one color that can color two sides, right? So we'll brute force over two sides that will take the same color. So I am calling A1 and A2 as the two sides that will take up the same color. So again, I'm looping over A1 and A2 from 0 to 4, and all the cases where A1 is equal to A2, I'll just continue. And then C and D will be the remaining two sides that will not be of the same, that would be of these two colors. So this is C, this is D, this is A1, A2. And again, I have ensured that all A1, A2, C and D are distinct from 0 to 4. And then in the end, what I'm doing is length of A1 plus length of A2, basically this, is equal to color I. So I am checking if the color I can be used to color the A1 and A2 sides, and then the C side will be colored using the jth color, and D side would be colored using the kth color. And if any combinations passes this if check, then that means that combination would be used to create the answer for 4, because we have found one color I which can color A1 and A2 sides, and we have found one color J which can color the C side, and one color K which can color the D side. And since all of them are unique, then this case would give us the answer 4, so we can set the answer as 4. And then to check if the answer is 5 or not, we can just run a for loop from 1 till 2 to the power 4 minus 1. So actually 000 is not good, obviously, because 0000 total length is 0 only, and since every color is at least 1, so this is obviously not good and we can skip that. So we'll check from 1 till 1111, and we can see what we'll do is we'll first calculate the sum of all the lengths that are 1 in the mask. So we'll check for I equal to 0 till I equal to 4. If mask has that bit set, then we will add that length to the sum. And if in the end sum comes out to be equal to R or equal to G or equal to B, then the answer would be 5. And initially I had set my answer to 6. So in the end, I'll just see out my answer. So whatever best case we found would be the answer. So that was the solution for problem C. If you guys have any doubts, you can ask. Yes, this question is of no topic. Yes, please. Sir, could you please repeat previous slide? So actually, from where did you guys not listen? Just someone tell me and I'll explain again. And if you guys actually understood, then it's fine. Explain again why answer can't be greater than 6. Oh, so I'll just so basically we have this sort of rectangular fence, right? And just the nearest process that we can think of would be just start from this corner and just start with the red color until the point you are using this red, till the point you are able to use this red color. Let's just use this red color, and then we'll switch on to the green color, and then we'll switch on to the blue color. So if we follow this strategy, we will be having a maximum of one intersection between the red and green and one intersection between the green and blue. So there will be only these two intersections, and each intersection will increase our answer by one, because here this side score was one, and because of intersection on this side our score became two, and again on the intersection because on this side the score became two on this side, and the score was one on this side. So the answer for this case would be 6. So we can just use this strategy and ensure that the answer can never be greater than 6. Isn't bit masking an overkill? It is generally quite easy if you want, if you are having small numbers and want to iterate over all of the permutation, all the combinations. So yeah, you can actually do 4 for loops instead of this also, and that 4 for loops can brute force over the combinations. How to solve this kind of problem, what's the thought process, where to start? So you can just start at the test cases, and first of all, if you're solving a test case, you will obviously use this naive kind of method where you just start coloring from one side to just see what kind of process, what kind of greedy, or what should I do. You'll start somewhere, right? So you'll just use this basic coloring algorithm, and you figure out that if I use this algorithm, the answer would be at maximum of 6, right? And when you, in a question, if you encounter this kind of thing that the answer could be only from 4 to 6, then usually the best possible way to proceed is that can we check for if the answer is 4 or if the answer is 5? And again, those came out to be pretty easy, and that's how you solve this problem. And overall, this problem is not actually very, I found this problem to not be good because it doesn't really use any logic apart from that the answer cannot be greater than 6. Otherwise, it's like simply implementation only. So yeah, you don't worry about this problem much if you weren't able to solve it. Is more constructive. So I'll wait a minute and then move on to the next problem. Okay, so let's move on to the next problem. I don't think there is any more doubts. So the next problem is three strings problem, easy version. Let P, Q, and R be binary strings of equal length L. Define P, F of PQR as the minimum total cost to transform Q into R using the following rules. So you may flip Pi or Qi for any index I, and each flip changes 0 to 1 and costs 1. After all flips are completed, you may perform any number of valid swaps in the resulting string Q at zero cost. A swap of indices I and j in Q is valid swap if and only if the final values of Pi and Pj are equal. It can be proved that it is always possible to transform Q into R using the above rules. You are given three binary strings ABC of length n, compute FABC. And the constraints for this problem are n is given till 1e5 and the sum of n over all test case will not exceed 1e5. So expected time complexity would be n log n. So in this problem D, we have three strings and we need to calculate the f of A, B and C, A, B, C. And what is this f of ABC? Let's define it. So it is basically minimum total cost to transform Q into R using the following rule. So minimum cost to transform B to C. So we need to transform from B to C and its minimum cost is defined as f of PQR. I'm audible, right? Yes. So what are the different operations we can perform? One of the operations is that we can flip Pi or Qi. So first operation is flipping Bi or Ci, uh, sorry, Ai or Bi. So cost is 1. And the second type of operation we can perform is after all flips are completed, you may perform any number of valid swaps in the resulting string Q at zero cost. So after all the flipping, what we can do is we can perform swaps between indice I. We can swap between Bi and Bj if Ai equal to Aj. So if final values of Pi and Pj are equal, we can swap I and j in Q. So if Ai equal to Aj, we can swap Bi and Bj. Bi and Bj. So let's see the test cases. So the first test case is simply 0, 0, 0, and since the string is already equal, we don't need to perform any operations. The answer is 0. Again, in the second test case also, we don't need to perform any operations, so the answer is 0. In the third case, we have 1, 1, 0, 0, and 1, 0, 1, 0, 1, 0, 0, 1. So in the third case, we see that we can, since this is the string A, B, and C, so let's just see if the answer can be 0 or not. So for the answer to be 0, we cannot make any flips and we can only perform these swaps. So since A and A are same here and A and A are same here, so we can make swaps on these two indices and we can make swaps on these two indices. And we can see that these two are already same. And here if we perform this swap and make it 0 this and make it 1 here, so this string will also become same. So after performing the swap, we can make B and C as same. So we don't need to do any flip operations, and so we can just perform the swaps of where AI is same. So the answer will be simply 0. And the conclusion that we can draw from this test case is that if the number of pairs 1, 0 is equal to the pair 0, 1, where AI is equal to 0, and similarly if 1, 0 is equal to 0, 1, where AI is equal to 1, then we can get answer with 0 flips. So what does this mean? Is that we can look at the pairs where AI is 1. So here AI was 1 and we had these two pairs 1, 1 and 0, 0. And here AI was 0 and we had these two pairs 1, 0 and 0, 1. So here the pairs were already both pairs are already equal, and here what we had is the number of pairs 1 0 were equal to the number of 0 1 pairs. So we can actually swap all the ones with the zeros and we'll be able to get the perfect string. So in this case, we can get the answer with 0 flips. So actually, because of this test case, what we have now found is what is the aim of these flips. What should be the aim of these flips such that after performing all the flips, we can get the B array, B string equal to the C string by just performing the swaps. So after the flipping thing, what should be now the new condition over B and A and B? So this must be that the number of 110 must be equal to, so these brackets will, let's just say for now that they represent the total number of indices where it is 110. So AI is 1, BI is 1, and CI is 0. This should be equal to the number of 101, and 001 should actually, let me do 010 must be equal to 001. Because if these two numbers are equal, these two equations are true, then we can perform the swaps under AI is equal to 1 and under AI is equal to 0, so that to make B and C equal, because we can swap out this 1 and this 0, and similarly here. So this must be the final outcome after performing all the flips. So let's see the next test case. So 11111 01010. And this. So let's actually write it out in this format. So we have 010 here and here and here. So we have 010 three times, and we have 011 two times. So actually 011 doesn't really matter to us, because we will not be obviously performing any operations on the 0 and on the 1 1 pair, because making this 1 as 0 would be simply increasing the answer for us, and switching this with any other 0 would also be not beneficial to us in any way. So let's just leave this out. So the count of 010 is 3. So the count of 010 at this one is 3, and the count of this one is 0, and these two are also 0. So this equation is satisfied since both of them are 0, but this is 3 and this is 0, so this is not satisfied. So what we can do, so we have two types of flip operations, right? We can either flip the bit in A or we can flip the bit in B. So let's analyze both of them. So first let's do the analysis on flipping AI. So we have four different type of cases where we need to be performing these operations, right? So we have 110, and we have 101, and we have 010, and we have 001. So I'm audible, right? Let me check. Yes, I'm audible. So for now, let's just name this as x1, x2, x3, and x4, right? So the number of these, this is equal to x1, the number of this is equal to x2, the number of this is equal to x3, the number of this is equal to x4. So what does flipping AI does? So if I flip AI in at this index, so this will transform to 010. So when this transforms to 010, what I have basically done is I have x subtracted 1 from x1 and added 1 to x3. Let me, sorry. And x3, okay, x3 plus equal to 1. And when I perform the operation on this, it will make it 001. So what I have done is x2 minus equal to 1 and x4 plus equal to 1. Similarly, here what I would have done is x3 minus equal to 1 and x2 plus equal to 1. Here x4 minus equal to 1 and x2 plus equal to 1. So these are the four operations we can perform. These are the four operations that we can perform on the values of x1 and x3, and our final goal is to make x1 equal to x2 and x3 equal to x4. So final goal is making x1 equal to x2 and x3 equal to x4. And if we flip the bit in AI, we will be performing any of these four operations. So we can actually perform any of these four operations. And next type of operation is that flipping the bit in flipping BI. So flipping BI is quite obvious. So let's say I am taking a general case of 110. So this was what x1, and if I flip the bit in BI, it will become 100, and this actually doesn't concern us, and it isn't part of any x2, x3, or x4. So what I have done is simply reduce x by 1. So actually I have now boiled down my problem to this. I have to make x1 equal to x2 and x3 equal to x4, and in one operation I can do either of these two. I can do xi minus equal to 1, this would be flipping bi, and what I can do is x1 minus equal to 1 and x3 plus equal to 1, x2 minus equal to 1 and x4 plus equal to 1, and vice versa also for both of them. So basically x1, let me just do plus minus here and minus plus here. Okay. So if x1 I am adding 1, then x3 I will have to remove 1. So x1 I am adding 1, that would be, wait, okay, this is x1, right? I think, yes, this should be x1 because 110 is x1. My bad, this is x1. So these four, I can either perform this operation and I can either perform this operation. So now it is quite obvious if we take some pair of values of x1, x2, x3, x4. So let's say that x1 was equal to 2. Actually, let's look at it this way. So what we are doing is we want to make x1 minus x2 as 0 and x3 minus x4 as 0. So let's name this difference d1 and let's name this difference d2. So we want to make d1 0 and d2 0, right? So what does this operation make changes on d1? Let's try to find that. So we are doing x1 plus equal to 1 and x3 minus equal to 1. So plus 1 here and minus 1 here. So basically what we have done is d1 plus plus and d2 minus minus. And had we done x1 minus 1 and x3 plus 1, this would be minus 1 and this would be plus 1. So that would be d1 minus minus and d2 plus plus. And similarly, if we do x2 plus 1 and x4 minus 1, so x2 plus 1 and x4 minus 1. So when I do x2 plus 1, I'm actually subtracting 1 from d1 because there is a minus here. So d1 minus minus, and again for minus minus plus, d2 plus plus. And similarly, x2 minus 1 and x4 plus 1, minus 1 plus 1 would be this case because minus minus is plus, so d1 plus plus, and plus minus is minus, so d2 minus minus. And xi minus equal to 1 would be simply, if I'm doing x1 minus equal to 1, then d1 minus minus. If I'm doing x2 minus equal to 1, then d1 plus plus. So the three different operations we can do is d1 plus plus and d2 minus minus, or d1 minus minus and d2 plus plus, or d1 minus minus, di minus minus, or di plus plus. These are the four different operations we can perform, and we need to minimize the total number of operations so that d1 is equal to 0 and d2 is equal to 0 in the end. So currently in our this test case, we saw that x 0 1 0, right? 0 1 0. So x1, x2, x3, I think, yeah. So x3 was 3 here, and x1 was 0, x2 was 0, x4 was 0. So our d1 will be x1 minus x2, which is 0, and d2 will be x3 minus x4. Sorry, this is 3, which will be 3. So d1 0, d2 3, right? Let's try to analyze it down here. So d1 is 0 and d2 is 3. So obviously d1 is 0 and d2 is 3. And what happens if we perform this operation? So that will make it -1 and 4. So I think we are going away from the answer. So we will not do this operation. What if we try to do this operation? That will make this -1 and this 4. My bad. In the last test case, in the last operation, d1 will become 1 and d2 will become 2, or this will become -1 and this will become 4. Or what we can do is simply three operations on d2 of this type. So we have an answer of 3 already if we just use this operation. And what we are seeing is that applying this or this operation isn't doing us any good, because here, even if 3 is approaching 0, this 0 is approaching away from 0. And similarly in this case, both the 0 and 3 are approaching away from 0. So actually we don't want to perform this operation since it is not doing anything. But if we look at this carefully, we'll notice that if d1 was a negative number -3 and d2 was a positive number like 4, then applying the operation d1 plus plus and d2 minus minus would be quite beneficial for us, because where this kind of operation can only change the value by 1, applying this operation, what this will do is it will make d1 as -2 and d2 as 3. So we have made two constructive changes, because -2 is closer to 0 than -3 and 3 is also closer to 0 than 4. So what we'll do is we'll perform two more operations of this type, so that d1 becomes 0 and d2 becomes 1, and then we can simply perform this operation. So this strategy would be the most optimal strategy, because we saw that if one of them is 0 and one of them is non-zero, it is better to just use this operation. And if one of them is negative and one of them is positive, we can actually converge them both towards 0 until one becomes the number 0 itself. So then for the other number, we'll have to perform again this type of operations. And the third case is if d1 was also positive and d2 was also positive. So now applying these operations will again not do anything, because they will just diverge us from the answer. So in this case, the most optimal will be 3 plus 4 only. So we can actually write this in code as well. What we can do is, if d1 into d2 is positive, so that must mean that both are of same sign. If both are of same sign, then these two operations are useless for us. So in this case, the answer is simply absolute of d1 plus absolute of d2. And if d1 into d2 was negative, then that means they are of different signs. Then we can actually, for this case, -3 and 4, we can actually perform this operation 3 times, which is the minimum of absolute of 3 and 4. And then for this, we'll perform this operation once. So what we can do is absolute, sorry, minimum of absolute of d1 plus d2, absolute of d1 comma absolute of d2, and then plus the left over. I'll show you guys the code. So I'll show you guys the code now. So first of all, I am simply counting x1, x2, x3, x4 as 0, 0, 1, 0, 1, 0 and 1, 0, 1, 1, 1, 0. And then I'm taking d1 as x1 minus x2, d2 as x3 minus x4. And then if d1 into d2 are negative, then that means they are of the opposite sign. So we can add 1 and -1 from them both, so that they both converge towards 0. So what we'll do is we'll perform this operation minimum of absolute of d1 and absolute of d2 times. And after performing the this operation x times, we'll have this value reduced by x and this value also reduced by x, and one of them will become 0, and we can just add that to the answer. So since one of them is 0, we'll be adding the leftover only. So just like in this case where we had -3 and 4, it became 0 and 1 after performing the operation 3 times, and then we just add 1 and 0 to the answer. So this, and else if both were of the same sign from the beginning, then the answer would be simply d1 plus d2. So that was the solution for problem D. What about D2? Have you checked the editorial? If yes, can you explain a bit? Actually, I didn't get the time for solving D2, but I think D2 was not solved much. Mm, So actually, D2 had only 30 solves even in div 1, so I think it would not be beneficial for most of you discussing D2 here, since generally solving problems within your rating range plus minus 200 is beneficial rather than solving problems which are too difficult for you. So we'll not be discussing D2 today. So if you guys have any doubts till D, you can ask. So, okay, I don't think you guys have any doubts. Um, I'll wait another minute. Okay, so I'll end this discussion. Thank you guys. Bye.